Okay, so now we will take a deep dive into a slightly in optimization, where we will not necessarily work with only linear algebra, but we are going to work with arbitrary functions, and linear algebra will be used to solve some of these problems and so on. And but the problems, then you may not end up getting linear equations. I must warn you about that. So I'm just going to talk about vector calculus. We'll assume that f is a continuous function. I mean, f is a function from end Rn to R, so it means it's a single real valued function. It is also assumed to be continuous, sufficiently smooth, so which means all the derivatives, as many orders as we want, we assume that the derivatives exist, the partial derivative. Now, if you take f as the standard cases, f as f of x versus R, you can plot graphs and so on. We know intuitively what is the meaning of continuity, what is the meaning of differentiability means there is no sudden jump, or there are no kinks. Continuity means it is smooth. Similar notions hold good when you talk about functions in two variables and so on. However, now it becomes slightly more difficult to appreciate functions of several variables. So one of the things we can do is, I could plot, this could be my xy plane, and this is my f. So in this case I get a three-dimensional, I need to work with 3 dimensions to look at how f behaves as a function. Suppose f is from R2 to R. Then I have to worry about doing things in 3 dimensions. And as you can see, I have a tablet over here, and then it's far more easier to work with 2 dimensions. So what I do is, I look at x1, x2 I look at only 2 axes in the 2-dimensional thing, but I consider f of x equal to c. That is a locus of all points such that which have the same value of f which is equal to c. So you may have seen a weather chart. Right? A weather chart will have isotherms, isobars and so on, which are all the points which have the same value of the temperature if it's an isotherm. If it's an isobar, it is all the points which have the same value of pressure. So likewise, I am going to assume that I can all these, something like this, just ignore this kink over here. So all of this has the same value of f of x equal to c. And let's call, so for some value of c1, I have plotted all the locus of all the points, and this happens to be, in this case it happens to be a closed curve. We will see that it doesn't always have to be closed curves, it could be, the curves need not be closed and so on. So all the locus of all points for which the function value is equal to c1, I plot this. So what is the advantage? I can still continue to do things in 2 dimensions. Now for a different value of c1, I will get another curve, f of x equal to c2. Now C2 could be larger than C1 or smaller than C1, it does not matter, but it is distinct from C2 is not equal to C1. That much is clear, otherwise it would have been the same curve. Now, let me clean this up. Now, I am going to look at, I have a point over here. I am going to ask, if I go along this curve, what happens to the value of the function? The value of the function does not change. If I go along this curve, the value of the function does not change. So let me assume that I am at some point x star, and I go to a neighboring point, which is by doing a I go a very small distance to a neighboring point on this curve itself. But the value of the function does not change. Right? So what do I get? I go to the new point. So you know that if I have to go to a new point by a small infinitesimal amount, the value of the function should not change, which means I should be really going along the tangential direction. If I go along the tangential direction for a large amount, the value of the function will change. For instance, if I go all along over here, this point corresponds to some other point for which f of s is not equal to c1. But if I go very, very small value along the tangential direction, the value of the function does not change. So again, you might have think about, if you recall this, you have also seen this in physics. Along these points, the value of the function does not change. The speed is or the velocity or the speed is along the tangential direction. If you go, the value of the function does not change. Now, if I go along some other direction, right? If I go along this direction, the value of the function, a small amount, even though I have drawn an exaggerated size for this displacement figure, in reality I am really going a very small amount along this direction. If I go along this direction by a small amount, the function will change. If I go a very small amount along this direction, the function changes. If I go along a very small amount in this direction, function changes. But if I go along very small amount along the tangential direction, I will continue to hug the curve and I will be on the curve. And if I am on the curve, the value of the function does not change. So from this point there are different directions in which I can go, and on some directions the function changes, some directions the function does not change. Along the tangential direction, infinitesimal changes if I make, the function value does not change. So I can ask this question, along which direction does the function value change the most, and along which direction does it increase the most and decrease the most. So I can define what's called the gradient vector, which is denoted by this, and this is basically the vector of the partial derivatives, because it's a function of two variables. There are two partial derivatives, del f by del x1, del f by del x2. It's a two-dimensional vector. Remember, what is a vector? Basically, a vector also tells me it's a two-dimensional vector, so I can plot this vector over here, and so on. What the gradient vector is telling me is, if I am over this point, it points in direction of maximum increase. Along the tangent, if you go a very, very small amount, the function value changes hard, it doesn't change at all, because I continue to remain on the curve, and all points on this curve the function value does not change. If I go along grad f, the function value increases the most. Likewise, if I go along minus grad f, the function value decreases the most. This is called the gradient. It is a direction of maximum increase locally. It does not mean that if I go a very large amount along this direction, the function value should have increased the most as opposed to all other directions. All of these are local concepts. Locally, if I go along the gradient, amongst all possible directions, the function value would have increased the most. So another way to think about this is, if you are at this point and you draw a circle of some small radius, and then you go along different directions like this, and then you record what has happened in the value of the function. Compared to this, if you compare what is the value of the function, the other new points, if you had gone along gradient, the function value would have increased the most along the gradient. If you had gone along minus gradient, along the negative of the gradient, the function value decreases the most along the negative of the gradient. So gradient is the steepest ascent direction, and negative gradient is along the direction of maximum decrease locally, which means I am allowed to make only very, very small changes. Now I can also have, this is in some sense like a derivative. Now derivative, however, does not, for functions of several variables, the derivative is a linear function which goes from Rn to R. Therefore, the derivative will be the transpose of the gradient. We will not worry about that, but the derivative is in some sense, the gradient is in some sense taking into account first derivative changes. I can also have second derivative information which I can capture, which I capture in a matrix called the Hessian. So the Hessian is a symmetric matrix of size n cross n. It is a symmetric matrix because, as I said, when the function is sufficiently smooth and derivatives exist, there is one fact that the partial derivatives, does not matter in which order you take, del 2, it does not matter whether you take it first with respect to I or with respect to j. Right? I am writing it in the symmetric form over here. So the entries along the diagonal are the second partials with respect to each of these individual variables, and the others are all mixed partials. So this is a symmetric matrix. It's a Hessian. It in some sense conveys second order information. If you recall functions of one variable, derivative tells you how fast functions is changing. Second derivative gives you an idea of the curvature. Likewise, in functions of several variables also, the gradient tells you in which direction the function value changes the most. The Hessian tells you something about the curvature of the function. Okay. So now we are all familiar with Taylor's theorem as functions of one variable. So f of x plus h is approximately equal to, for as long as the function is sufficiently smooth, the derivatives exist and so on. You can be more precise and put either remainder term or bound the size of the remainder over here. This is functions of one variable. Now it is functions of several variables. Obviously you cannot do this. We will work with certain Taylor series approximations up to second order approximations, and what we will write is f of x plus h, where x is a vector of size n cross 1, h is also a vector of size n cross 1, f goes from Rn to R. So I have to be very careful about how I write these things. So this is approximately equal to f of x plus gradient of f, okay, transpose h. Remember the order is, because these are matrices, vectors now, so I have to make sure that it makes sense. This is gradient of f transpose is 1 cross n, this is n cross 1, that makes sense, it's a number. So this is 1 cross n and this is n cross 1. This is of course a number. Now for the second order term, I have to be very careful about how I write this. H transpose, the Hessian, the Hessian also I denote it as del square. I mean like this is how I denote the Hessian. I go Hessian as h in the previous case, like more generally it is denoted as, this is how the Hessian is denoted, and there are other remainder higher order terms. This is the kind of expression that I am going to use for deriving some of the concepts that we need when we ask for finding out function minima and maxima of functions and so on. And this completely makes sense, right? H is a vector of size n cross 1, so H transpose is vector of size 1 cross n. This is a symmetric matrix of size n cross 1, and this is a vector of size 1 cross n. So this is a number. So I am going to assume that the others are, there are remainder terms or higher order terms. I can usually denote it as, I can usually bound this as, which are cubic in the size of h. Okay, so now this is about multivariable vector functions of several variables. I am not worried about vector valued functions. I am only looking at functions of several variables which takes a vector to give me a real number, right? And why am I interested in this? I am interested in this because we did some, when we did the least squares problem, we talked about completely from a purely linear algebra geometric point of view, trying to find shortest distances, we are trying to minimize distances. Now in an arbitrary setting, what I am usually interested in is, I have a function, this is the kind of problem that I am interested in is, I am interested in finding that I am interested in finding that x which gives me the least possible value for f. Just as in the previous least squares problem, shortest distance problems, I am trying to minimize the distance. In that case, the problem turned out to be a nice linear solution system of equations, but in general situations that is not going to happen. I may be interested in finding the minimum of a function of several variables. We all of us know how to find minima of functions of one variable. So derivative equal to 0, and we check for the second derivative, if it is positive we know it is a minimum, and so on. And then we have likewise for functions of several variables, I am interested in finding out what value of x gives me the least possible value of the function of f. And this is going to be very useful because I am trying to do, usually when you solve engineering problems, I am trying to find a design or a product or something which is best in some sense, either in terms of cost or price or best in terms of fuel economy and so on. In the case of data analysis, it's usually in terms of trying to best explain the data. I'm trying to find the best possible explanation for, or the best possible classifier and so on. All of these things which will be dealt in detail by some of our colleagues. But this is going to be a problem that will come up in several times. I have given several variables x which I can vary. Those are my so-called degrees of freedom. And I'm trying to find out that, and I'm given a function which takes each of these values vector and gives me a real number. I'm trying to find that value of x which minimizes this f. Now, first thing is, what is a minimizer? And I am going to assume that f is continuous, smooth, and so on. It's just nicely behaved. So, a local minimizer, x star is a local minimizer. If around x star, there is a small neighborhood. Neighborhood means a certain, you can think about it as a ball around x star. I don't worry about how big or how small. All I am claiming is there should be a small enough, you should be able to find at least one neighborhood around x star. If it is a local minimizer, then f of x should be greater than f of x star for all x not equal to x star and x in the neighborhood. This is a local minimizer, which means at least locally I am able to find a good, the best possible value. For instance, if I am trying to find, let me talk about, I am trying to find the large, on the surface of Earth we know that Mount Everest is the highest point, is on 8,848 meters, but I'm not going, suppose my eyesight is not so far, I have never been out of Goa. You can always find out what is the highest point in Goa. There is definitely points which are higher than that point, but definitely within Goa you can find a highest point. At least you can see that within a certain range, if you agree not to go beyond a certain radius around that point will be the highest point. Likewise, in the case of minimizers, we are usually interested in trying to find minima or functions. I am trying to find that value of x star such that f of x, for all the other points, it should be higher value of, larger than or equal to. It could be equal to, but it should definitely not be smaller than that of x star. Then x star is a local minimizer. Now f star is a global minimizer if f of x if for all other points you cannot find any other better point in terms of the value of the function, then it is a global minimizer. Likewise, you can also define local maxima and local maximum and global maximum, which is just the converse. It is just we talk in terms of the sense of direction gets reversed in this case. Now, I am going to quickly tie up what are called the necessary conditions of optimality. Just as we know for functions of one variable, the derivative equal to 0 is a necessary condition. The necessary condition for optimality. So now if you go back to the necessary, what did we say for a local minimizer, x star, you go a small amount, I should be able to find a neighborhood around x star, no matter which direction I go. The value of x, f of x, should be greater than or equal to f of x star, right, in some neighborhood. I'm not even talking about, I'm only talking about local optimality. It's always, lot of these characterizations can be possible only for local optimality. Now, what do we know about it? What it says is, no matter around x star, that is, no matter which direction you go, the value of the function should always be larger than or equal to that at x star. Now, what do you know about the gradient? Gradient tells you the direction of maximum increase. The gradient, negative gradient is direction of maximum decrease. Now, my claim is this: the gradient has to be 0 for a local optimum. This is a necessary condition. Why? Because if the gradient is not 0 for a local optimum, you can go along minus grad f. And what happens along minus grad f? The function decreases, in fact decreases the most. So if you go along minus grad f a small amount, no matter how small you go, the function value will decrease. But it contradicts my definition of a characterization of a local optimum. So the gradient should be equal to 0 it's a necessary condition for local optimum. So this is also usually called first order necessary condition. Now, is this enough for me to decide whether it's a minimum? No, unfortunately no, because the same thing holds for a maximum also. This is for a minimum. For a maximum, what does it say? Local maximum. You go a small amount around x star, f of x cannot be larger than that of x star. It can be less than or equal to at x star. This is for a maximum. Use the same argument. For a maximum also, gradient should be equal to 0. Why? Otherwise you can go along grad f and the function will increase. In fact, increases the most along direction. So gradient equal to 0 is both for maximum and minimum, and there are also other kinds of points called saddle points, such that if you think about a saddle, right, a horse saddle or a mountain pass, along some directions the function increases, along some directions the function decreases. We may come to that later, but saddle points are also another kind of stationary points for which the gradient equal to 0 is it happens that the gradient is equal to 0. So these are only necessary conditions but not sufficiency. So you need to look at second order conditions, and that is why Taylor's theorem is useful. So let's say x star so what do we know? This is a necessary condition, which means gradient of f evaluated at x star is equal to 0. So now I will do a Taylor series expansion around x star. So that will be f of x star plus h is approximately equal to f of x star plus gradient of f evaluated at x star this is the Hessian evaluated at x star plus higher order terms. Right? I know that at x star is a local minimum, so this is equal to 0. So f of x star plus h minus f of x star is approximately equal to half plus higher order terms. There will be higher order terms, which I can bound it as. Right. Now remember, I am only interested in local minimum. I am only interested in local properties. So what I am going to claim is, for it to be a minimum, what can you tell me about the sign of this guy over here? It has to be non-negative, right? This has to be non-negative for this, for it to be a minimum. Now my claim is, because I am only interested talking about in terms of local minimum, I go very small amounts of h, and eventually there will be small enough neighborhoods where the sign of this guy will only depend on the sign of this. What that means is, this should be positive. Suppose there is something for which this is negative, what I am claiming is that if I decrease my h small enough, the sign of this term over here will be dominated only by this, because this grows as as h cube, this grows as h square, as h only, as h square. This is of order of h square, this is order of h cube. And then when h becomes smaller in size, finally this term will dominate over this. When h becomes very small in terms of the numbers values, and when h becomes very small, you can neglect this guy in comparison to this. These are very rough intuitive arguments, not very formal arguments. Therefore, if I want to look at the sign of this, it is enough just to look at the sign of this for very small values of h, and it is perfectly allowed, because I am only interested in local properties over here. I am not talking about what happens when I go very far away from x star. I am only interested in talking about what happens very close to x star. The sign of this guy will be dominated by the sign of this. So for this to be non-negative, this has to be greater than or equal to 0. So for this to be non-negative, this has to be greater than or equal to 0. So this is called the second order necessary condition. What this means is, okay, I should have probably done that. So this is the Hessian matrix. It says that the Hessian, and this depends, even though h can be of any size, it can be in any orientation. So no matter what orientation I take, this has to be greater than or equal to 0. This means that this matrix is positive semi-definite. What I am going to do is, I also mentioned this about being able to write things in terms of eigenvalues and eigenvectors and so on. So we will see what this means in terms of eigenvalues. Let us take a two-dimensional example, that is h is in R2. Right? So now this is a symmetric matrix. So what do we know about the symmetric matrix? The eigenvalues are real, and you can find perpendicular eigenvectors. So let V1 and V2 be lambda 1, lambda 2 be eigenvalues, and let these be eigenvectors. V1 and V2 are eigenvectors, and these are eigenvalues. Okay, let me again clear this out. So this is my second order necessary condition. Right? Let's take f is from R2 to R. V1, V2 are my eigenvectors, lambda 1, lambda 2 are my eigenvalues. We know they are real, and V1 and V2 are perpendicular to each other. So what do we know about that? V1 transpose V2 is equal to 0. Now because they are independent eigenvectors, and this is in two dimensions, my h can be written in terms of H can be written in terms of V1 and V2. It doesn't matter because they are independent eigenvectors, and moreover I know that V1 is perpendicular to V2. So let me expand this out. So I can forget about the half over here. So this is alpha 1 V1 plus alpha 2 V2 transpose is the Hessian matrix times alpha 1 V1 plus alpha 2 V2. Let's just try to expand this out. So this you will get alpha 1 V1 plus alpha 2 V2 transpose alpha 1 is a scalar, so I can bring this out over here. Likewise, alpha 2 is a scalar, so I can bring this out over here. What do I know about this? This is a Hessian times the eigenvector. So what is it equal to? Hessian times an eigenvector, matrix times an eigenvector is equal to eigenvalue times the eigenvector. So this is just equal to alpha 1 lambda 1 V1. V2 is an eigenvector. So Hessian times that eigenvector is equal to alpha 2 lambda 2 V2. Right? Now, when I expand this out, this is transpose this, I will get 4 terms, but that will be some, let me see what all I get. Alpha 1 is a 2, so I get alpha 1 V1 transpose alpha 1 V1. Let me write out the easier terms first. Right? Then there will be a cross terms, this multiplies this. So alpha 1 V1 transpose, oh there is also an lambda 1 and a lambda 2 over here. So alpha 2 lambda 2 V2 plus alpha 2 V2 transpose alpha 2 lambda 2 V. Right? And these are all scalars. Alpha, lambdas are all scalars. The only vectors are V1 and V2, V1 and V2. What do we know about V1 transpose V2? 0. V2 transpose V1 is also 0. Right? So this goes to, all of this goes to 0, this goes to 0. So I can ignore this. So this has to be greater than or equal to 0, and this is equal to, so let me simplify this, equal to alpha 1 square lambda 1 V1 transpose V1 plus alpha 2 square lambda 2 V2 transpose V2. This has to be equal to 0 for all my H over here, right? I am not worried, I am only worried about the size of, all directions of H, it has to be equal. So what can you say about lambda 1 and lambda 2? Which means it definitely has to be equal for, it has to be, no matter which direction I go, this term should be non-negative. Definitely it should be true for, I go along the eigenvector directions. If I go along the eigenvector directions, if I go along V1, then alpha 2 is equal to 0. Because I am going only along the first eigenvector directions. So which means I put alpha 2 equal to 0. So what do I get? Alpha 1 square lambda 1 V1 transpose V1. This has to be greater than or equal to 0. Put alpha 1 equal to 0. So you get alpha 2 square lambda 2 V2 transpose V1 greater than or equal to 0. This is a non-negative number. The length of a vector is, this is definitely positive in fact, because we said eigenvectors have non-zero vectors, they have non-zero length. So this is positive, this is positive, therefore this has to be, lambda 1 has to be non-negative. Likewise this is positive, so therefore lambda 2 has to be non-negative. So the second order necessary condition is, let me concisely write it down, eigenvalues of Hessian are non-negative, or such matrices are called, the symmetric matrices. such matrices are called positive semi-definite matrices. So the first order necessary condition is gradient of f equal to 0. Second order necessary condition is the eigenvalues of the Hessian matrix are non-negative. To give you a rough parallel, for functions of one variable, the second derivative should be non-negative, right? For functions of one variable, derivative equal to 0, second order necessary condition for second derivative should be non-negative. It is exactly a parallel of that, because now, however, the second derivative is not a number. The second derivative information, everything is captured in terms of a Hessian matrix. So the eigenvalues of the Hessian are non-negative, or Hessian is positive semi-definite. Then if this is called a second order sufficient condition, which means the problem with this necessary condition is there are cases in which the matrix is positive semi-definite, the gradient is 0, the matrix is also positive semi-definite, but you don't have a minimum. You could have a saddle point, you may not have a minimum. That is, you may go along some directions, the function value could decrease even if you go a very, very small amount. So that's why it is only a necessary condition. So sufficiency condition is if all the eigenvalues are Hessian are strictly greater than 0, which means greater than or equal to 0 means some of the eigenvalues could be equal to 0, but if the eigenvalues are strictly greater than 0, then the matrix is called positive definite. If the eigenvalues of the Hessian matrix are strictly greater than 0, then it is a sufficiency condition. You know that you are at a local minimum. I am not claiming anything about global minima at all. I am only talking about all of these characterizations are only for local minima, which means I do not know if I reach the topmost point of Goa, I don't know whether I really reach the topmost point of even India or the world or anywhere. Whether the topmost point in the world is definitely Mount Everest, which is in Nepal. Somewhere else is definitely there may be a peak which is higher in altitude in one of the neighboring states. But all I am characterizing based on this is if I am only able to characterize local information. Or equally within the Goa University campus, you may be able to find out one point which is at the highest point. That may be the local maximum. It may not even be the tallest point in Goa. Or within this room, I can easily find which is the topmost. If you ignore that, if the surface has some slight ups and downs, there may be a point which is the topmost point within this room. But it may not even be that, definitely it is not the topmost point within the building. So likewise, I am only characterizing local optima over here, not global optima. Only for certain classes of functions can this be very nicely characterized, and unfortunately many of those functions are not those. Many of the regularly observed functions may not be of that kind, but for many of the functions we can only characterize if this is the Hessian is positive definite and the gradient is 0, we can only be guaranteed that we have reached a local minimum, not necessarily a global maximum. For a global minimum, for a maximum the signs are reversed. Eigenvalues have to be non-positive, and for a sufficiency condition, eigenvalues have to be strictly less than 0, or the matrix is called negative definite for a maximum. This is for a minimum, and for a maximum, everything, all the implications are, the directions of the signs are all reversed. Of course, the first order condition is the same, gradient is equal to 0, second order necessary condition is Hessian is negative semi-definite, which means lambda i's are less than or equal to 0. Second order sufficiency condition is Hessian is negative definite. All the eigenvalues are strictly less than 0 for a maximum. Okay, I think this is a good time also to stop.